I'm sure at one point or another you've heard about astronauts being generally weightless on the moon because of the gravity. I mean, according to Alan Shepard, you can hit a golf ball and it'll go for miles and miles and miles. But you'd think they find the value of gravity before they went up there, like Newton measured the rate of the falling apple on Earth. But that'd be completely wrong because they figured it out way before they stepped foot up there. And so, how did they do that, and why is it so important to know? Let's talk gravitation. Newton's law of universal gravitation is much like the most memorable equation from Physics 1, force equals mass times acceleration. But since we're talking the force of gravity, acceleration in this case, g, is 9.8 meters per second squared, the same acceleration that hit his head all those years ago. During that same epiphanic concussion, he pondered about if the moon's always there, is it also drawn to Earth with the same pull that made the apple fall? Luckily, that pull isn't accelerating at a rate of 9.8 meters per second squared, because then we'd have another ice age. So then, what is g? What is the strength of that pull? Even though Newton didn't know that value, he came up with this equation: the mass of one object times the mass of another divided by r squared, which is not the radius but the distance between the center of gravity, and all that multiplied by g, a gravitational constant which he knew existed but not exactly what it was. So how did we find g? The value that Newton just didn't quite know at the time. That's where the Cavendish experiment comes. The Cavendish experiment is fairly simple. Two dense spheres are placed on a long rod, hung up by a thin wire in the middle so that everything is balanced, or so that the net force, or what we often consider as the net force, to be equal to 0. To complete the setup, another structure with two dense spheres is placed in a way so that there's a distance between the spheres on the rod. So once you had the timer going and didn't interfere with the spheres and tried not to create an air current, Cavendish found that the rod with the spheres started to gravitate towards the other spheres at a rate of 0.00000066743 units, or 6.6743 times 10 to the negative 11th. Before we start calculating our gravity on the moon, we have to ignore the mass of one of the objects we were calculating before because we're only focusing on one. Second, we have to change our understanding of r squared from being the different distance from the different masses, centers of gravity, to the radius of our planet, or moon, that we're investigating. As a result, we said g is being equal to the gravitational constant times the mass of our planet, or moon, divided by the distance between the center of mass squared. Let's actually solve for gravity. And once we plug in everything, we can find that the moon's gravity is 1/6 of Earth's. It's really important to know the gravities of these planets and moons before we land on them to keep from crashing into them, because gravity determines how fast we should descend or ascend off of them. For instance, Mars's gravity is 3.72, and we wouldn't approach it the same way as we do landing on Earth or the moon.